Professor Suresh?
Yeah. Thank you, Sajjad, for inviting me to speak in this conference. I also thank all other organizers and also the local people who are helping you. Okay, so I wish I've been there in person, but unfortunately I could not come there. Okay, this is about some local principles for projective homogeneous spaces. So if you don't understand any of the terms in the title, just forget about it. Okay, so as in the first talk, Nitin said, at least the first 20 minutes should be, everyone should be able to understand the talk. So let us hope I'll make that. At least in the next 20 seconds, everyone should be able to understand. So that's the next slide, which you can read it. This is a famous quote from Brahmagupta. So that's what I'm trying to do now, hopefully. Is it visible to everyone?
No, the slides are not moving.
Yeah, but I just put one slide. The problems. The Brahmagupta quote. Is there?
No, it's not there.
It's not there.
No.
Why? Now?
No. It's still on the local global principles.
Why?
In 20 seconds, I already passed by.
So everyone are able to understand the 20 seconds. I don't know why slides are not going. It's moving on my screen. Okay, so let me try again. So stop sharing. Is it okay now?
So it's not moving. It's not moving.
Oh, still on the local global principle?
Yeah. The first page only. Yeah.
Oh. Same now?
Yeah.
It's not moving.
The first page, yeah, but maybe you should use some other key to move to the second page.
Yeah, I'm moving. It's moving on my screen.
Oh, I see. You got it fixed here. Yes. Go to the previous page now.
Yeah, but now it's not in the full screen mode.
That doesn't matter. At least it doesn't matter.
Okay, let me try again. Balaji.
No, it's not in full screen. It's in small screen now. But at least it's visible, Maybe go to the second page and make it full screen. Yeah, now try. Yeah, it's not going to the full screen at all now.
Okay, just let me try something else.
Are you still trying?
Yeah, I'm trying.
Yeah.
I'm trying to connect from my iPad. No, nice. From my iPad, I'm not able to log in.
We just come to the small slide is okay, actually. It is easily visible.
So this is okay?
Yeah, this looks fine to me. One can read what's written there. That's important. I mean, the audience in the, now it's full. No, it's fine. But try to go to the, it's fine. Yeah, now it's fine. Full page.
Okay.
Yeah, you can start with your 20 seconds now.
Yeah, I make it a little bigger. Is it moving now?
Yeah, now going.
Okay. Now can you read all this, at least this 20 seconds for you?
Yes.
This is a quote from Brahmagupta. Okay, so I'm not. Yeah, now it's bigger, right? Okay, so let's start. So in algebraic geometry, so what is our main goal is to solve some polynomials, or not exactly want a solution, but try to see whether it has a solution or not. So classically, the algebraic geometry started like that, but most of the algebraic geometry is what the algebraic closed field or complex numbers. But in this talk, all our problems are trivially solved over such fields. So we look at other fields. So one would like to solve such equations. Of course, f is a polynomial with coefficients. We'll come to that soon, where the coefficients are. Okay, so let's look at some polynomials, examples. So if you look at this, of course, this is a solution for that. Everyone knows that. And more generally, if you take any degree 1 polynomial, so if you look at like this, if you want to solve this, and of course, one can solve this very easily, provided it is consistent. That is, if A is non-zero, at least one of the AI should be non-zero. Otherwise, it has no solution. Okay, so yeah, I think let me make it a little smaller. Okay, so from now onwards, we look at only the homogeneous polynomials. So let's see some more examples. So a homogeneous polynomial of degree 2. So we have summation aij, xi, xj, where aij's are in some field. So we'll come to that which field we are looking later, but in some field. So we look at such polynomials, and such polynomials are called quadratic forms. And of course, if you put all xi is equal to 0, then this is trivially a solution for this, and we call such a solution the trivial solution. Because it's a homogeneous polynomial, so 0 is always a solution for that. But of course, we are interested in finding some non-trivial solutions. Okay, so if you look at this homogeneous polynomial, it has plenty of non-trivial solutions, provided the field has enough elements. And if you look at this also has a solution. I think the bottom line is, yeah. So if you look at the polynomial x1 square minus x2 square, so 1, 1 or any a, a is a solution for that. And okay, so now let's change slightly more. So if you look at the polynomial x1 square minus a times x2 square, so is there a non-trivial solution for this polynomial? So non-trivial means at least one of the coordinates should be non-zero. And it can be easily seen that there is a non-trivial solution for this if and only if a is a square. So we get x1 square equal to a times x2 square, and you divide by x2 if x2 is non-zero, then you get a is a square. And if a is a square, you can see that it has a solution easily. So now let's look at homogeneous polynomial in 3 variables of degree 2. So let's make a little more complicated. So if you look at this polynomial, x1 square plus x2 square minus 3 times b square. So is there a non-trivial solution for this equation when you want to equate to 0? Yes. So now we have to see where we are working. So if you look at our reals, so 3 is the square over reals. So therefore, so for example, 1 comma 0 comma, square root of 3 comma 0 comma 1 is a solution for this, or reals or complex numbers. Now the question is there a non-trivial solution for this over field of rational numbers? So can you find some rational numbers a, b, c such that a square plus b square equal to 3 times c square, and at least one of the a, b, c should be non-zero? Okay, so let's see whether this has a solution or not. So again, the same question I'm repeating here. Okay, now suppose there is a non-trivial solution over the field of rational numbers. So then by clearing the denominators, we have a non-trivial solution of the ring of integers. So if suppose there is a square plus b square equal to 3 times c square, so write each a as a ratio of 2 integers and you clear the denominators. So you get again some m square plus n square equal to 3 times t square, where m and t are integers. Okay, so therefore looking for rational solution is same thing as looking integer solutions. So suppose there is a non-trivial solution over the ring of integers. Okay, so that means there exists some 3 integers, not all 0, such that a square plus b square minus 3c square equal to 0. Okay, now how do you see whether such thing exists or not? So that's our main question. So we need to use some local data. So without loss of generality, so let's say that a, b, c have no common factors. Because if there are some common factors, we can take it out and cancel it. So we can assume that they have no common factors. Now we're looking go modulo 3. So in Z mod 3, we have only 3 elements. And this a square plus b square minus 3c square is congruent to a square plus b square mod 3. And in mod 3, so the negative 1, which is 2, is not a square. So a square plus b square is congruent to 0 mod 3 if and only if a and b have to be 0. So if a is non-zero mod 3 and b will be non-zero mod 3, and from that you get negative 1 is a square, there is 2 is a square, and you can check that 2 is not a square mod 3. So therefore they have to be 0 mod 3. That means a is 3a1 and b is 3b1. So we have this. So substituting that, you get this. And then from this, it's easy to see that. So from this, we get that 3 divides c square, therefore 3 divides c. And so 3 divides a, 3 divides b, and 3 divides c. So which is a contradiction to our assumption that they have no common factors. So from this, we conclude that there is no solution, no non-trivial solution for this equation over the field of rational numbers. So to see something whether it has a solution or not, so we are going mod 3 and checking here. So let's look at one more example. So if you look at this equation, so by going modulo 11, we can, so again mod 11 we have only 10 elements and we know what are the squares and what are non-squares. So just writing them and making a big table, one can show that this has no non-trivial solution. But however, if you go mod 7, so if you go mod 7, 11 is just 4. So this is x1 square minus 4 times x3 square. So it's 2 comma, so the 2 square minus 11 times 1 is 0 mod 7. So that has a solution mod 7. But mod 11, it has no solution, therefore it has no solution over integers. But now let's look at one more example. Now, it's easy to say that this has solution over reals and complex numbers. So once we have solution over reals, then it has solution over complex numbers. So over reals, so this is a negative number, and so this is, so therefore the 6, whatever this number is a square over reals. So we get trivially non-trivial solution. It's easy to get. Okay, now how do you decide whether it is a solution over Q or not? Again, we can have integers, and one can check that it it has a non-trivial solution modulo n for all positive integers n, not only for prime. Of course, once you show for primes and powers of primes, from that and using Chinese remainder theorem, we get for all integers mod n. So this has a solution mod n for all positive integers and over reals. So then we are stuck. So how do we? So if it has no solution mod n for some n, then we can clearly say it has no solution over integers. Therefore, no solution over rationals. But this one has solution for mod n for all n and over reals. Okay, so now question is there a solution for this or not? So to answer this, let's develop some, make some definitions. So homogeneous polynomial of degree 2 is called a quadratic form, and a quadratic form is called isotropic if the equation has a non-trivial solution. That's what we are looking for, right? Non-trivial solutions. So once it has a non-trivial solution, we say it's isotropic. Otherwise, we say it's anisotropic. Okay, so there is a theorem of Minkowski, says that if you have a quadratic form with all integer coefficients, and if this is isotropic over reals and isotropic modulo p power n for all primes, p and n greater than or equal to 1, then it is isotropic over q or isotropic over z. It's the same, right? So this is a famous theorem of Minkowski. So from this, so if you go back to this one, so this has solution over reals and solution over p n for all integers, so in particular all powers of all primes. So therefore this equation has a solution over integers. Now if anyone interested, try to write down a solution for this one. Okay, so this answers that question, and this is more generally. So if you have a quadratic form which is isotropic over R and isotropic modulo p power n for all primes and for all n, then it is isotropic over Q. Okay. So now, but apparently this looks like there are infinitely many conditions to check. You have to check p power n for all primes and for all n. But let's make it this more formal. So let's introduce the p-adic numbers. So we all know that on Q we have this Euclidean norm, so that is the absolute value. And if you take the completion of Q with respect to this metric, is a field of real numbers. Now, are there any other norms on Q? Yes, there are many. So for every prime p, so we have a p-adic norm on Q defined like this. So take any rational number. So we can write it as a p power m times r over s, where r and s are integers and they are not divisible by p. So the maximum power of p comes out here. So this m could be positive or negative. And so you define this, there is a p missing here. So the p-adic norm of this is 1 over p to the whole power m, where this m is the maximum power of p which divides this. Okay, so this is a norm, this is a metric, one can check that. So, I mean, this is a norm and this induces a metric on this. And then once you have a metric, then we know the completion in topology. So we take set of all Cauchy sequences with respect to this metric and go modulo certain equivalence relations. And then you get a completion. Of course, in this case, one can show that this completion is a field. And this is a field of fractions of the inverse limit. There is something called inverse limit. Let's not worry much about that. Okay, so now let's rewrite the first theorem of this Minkowski, what we stated. So if you have a quadratic form, Aij, Xij with coefficients in Q, and if this is isotropic over reals and isotropic over QP for all the p-adic number in fields for all primes p, then it is isotropic over Q. So instead of checking mod p power n, so we're just checking over QP for all p. Okay, so even all p, there are infinitely many primes, so we'll come to that later. So it's enough to check only for some finitely many primes. In fact, it's enough to check for the primes which divide, if n is at least 3, it's enough to check for the primes which divide the Aij's. So there are only finitely many primes. Okay, so now this is completely solved this problem. So we want to check if quadratic form is isotropic or not over Q, you go to the QP. And how do you check over QP? So there is a way to reduce it to the finite field, Z mod PZ. And from there, we know there are only finitely many elements and you can check everything. And okay, so, okay, now instead of rational numbers, so we can take finite extensions of this. So fields which are finite dimensional over Q, they are called number fields. For example, adjoint square root of 2 to Q, or square root of -1, or square root of cube root of 5, or any finite extension. Now, the algebraic structures and problems relating to them have been classically studied over these fields, the many like quadratic forms. Instead of looking over Q, we can look at over these number fields, or division algebras, or many other algebraic structures. And once we want to study these algebraic structures, again, we want to go to some local global principle, like in the previous case. So this is called a local global principle. So instead of checking over Q, it's enough to check over QPs and reals. So is there an analogous thing here? Okay, so to understand this global picture, so our number fields, we want to look at the problem over locally, that is our local fields. So what are local fields? Finite extension of QP are called local fields. E.g., again, you can adjoin any square root, cube root, or any finite dimensional extension, they're called local fields. Now, if K is a local field, then there is a subring of K, it's called the valuation ring, with a unique maximal ideal M and field of fraction is K. Further, this R is the inverse limit, and R mod M power n is a finite ring. So in particular, R mod M is a field, finite field. So any finite extension, so QP has that property, like namely the ZP, which we defined there. And if that has a maximal ideal and you go mod that maximal ideal, there you get the FP, the field with P elements. But more generally, if you take some finite extension of QP, so we'll have some finite extension of FP as the residue field at R mod M. Okay, so and this in particular, this R is a complete discrete valuation ring. So that means, so there is a discrete valuation income. So in general, so what does it mean? There is a metric on this. And if you take any Cauchy sequence with respect to that metric, that converges. So there is a Hensel's lemma. We say that if a polynomial equation has a non-trivial solution over R mod M power n for all n greater than or equal to 1, then this has a non-trivial solution over R. So it's like Z and Z mod P, what we're looking there. So instead of that, you can look at here and R mod M power n. So this is the crucial lemma for which we are. So therefore, over these fields, so or these local fields, so we have better understanding of these polynomial equations. So we know when this is a 0 or not. It's enough to check go R mod M power n, and in many cases, it's enough to check over R mod M. Okay, so what is local to global? So we may replace Q by any number field and take omega k, the set of all places of K. So what is the place? Which are extensions of the norms on Q associated to primes and infinity. So on Q, we have defined the periodic norms and the infinite norm, the Euclidean norm, and each of them extends to a norm on this K. Of course, each extension extends to some finitely many metrics or norms. And you take set of all such norms, or what you call places. And for each norm, there is a completion, like again taking Cauchy sequences modulo certain equivalence relations. So this is a complete field, and this completion is a local field. When this nu corresponds to the finite primes, and if it is corresponds to infinity, then it's reals or complex numbers. So these are some extensions where there are local fields or reals or complex numbers. And the theorem of Asa and Minkowski says that if you let K be a number field and Q a quadratic form over K, if Q is isotropic over K nu for all nu in omega K, then Q is isotropic over K. So again, when you want to check some quadratic form is isotropic over this number field K, it's enough to check over all these completions. Again, when you say all completions, there are infinitely many completions, so we don't know how to check for infinitely many, right? So in each given a Q, there are only finitely many valuations where it's enough to check where it's isotropic or not. So in the remaining things, it's automatically isotropic. So given a quadratic form Q, so look at the aij's, and depending on those aij's, there are only finitely many places where we need to check. So therefore, this is only finite condition. Okay, so that's for degree 2. Now let's look at the next degree 3. So look at this polynomial, which is very nice 3, 4, 5. Now this has a non-trivial solution over reals. We can check easily because it's a degree 3, right? And of course, our complex numbers any non-constant polynomial is 0. So, and one can check that this is a non-trivial solution over QP for all primes P. So for degree 2 polynomials, that is quadratic forms, we know that if it has solution over R and solution over QP for all P, then it has a solution. But this is degree 3. And unfortunately, this is not non-trivial solution over Q. So this example was first given by Selmer. Okay, so what do you do? Now for degree 2 polynomials, we have this local Grover principle. That means locally, that means all at completions, if it has a non-trivial solution, then it has a non-trivial solution over globally. That means over Q or over number fields. And once you have degree 3 polynomials, then this is no longer true. So we want to see what is going on behind the scene. So why it's true for degree 2 and why it's not true for degree 3. So for that, we want to introduce algebraic groups. So take a quadratic form or any field. Let's assume characteristic is not 2. So most of the time we'll be working only with number fields or p-adic fields. So it's okay. Characteristic is 0 there. Now let this matrix associated to this quadratic form. So this is a symmetric matrix where the diagonals are just the ai and the other things are aij over 2, and you make it symmetric because these aij's are defined only for I less than or equal to j, and once j is bigger than I, so this is same thing as aij over 2. So this is a symmetric matrix, and let's assume that the determinant of A is non-zero. If the determinant of A is 0, so one can show that this polynomial, this quadratic form is isotropic always. So let's assume that determinant is non-zero. Now for any field extension, let the set denoted by SOQ of L, all those matrices of determinant 1 such that the P transpose A times P is A. So these are the isometries of this quadratic form. And then this SOQ is a connected linear algebraic group. So whatever, if you know what is linear algebraic group, it's fine. Otherwise, just think as a group for every field. So this is a subgroup of SLN of that L, of that field L. Okay, now let's look at projective quadratics. So for any extension L over K, let QL is a subset of P and L, the projective n space, with a solution set of QX1, X2, Xn. So what is this P and L? So these are the lines in the vector space Ln plus 1. So now if you have one solution, suppose A1, A2, An is a solution for this, then lambda times A1, A2, An is also a solution for this. Therefore, the line passing through origin and that point A1, A2, N is a solution for this. So we're just taking those lines. So this is QL is a set of lines which satisfies this equation. Okay, this is a projective variety, so called the quadratic defined by Q. And just by definition, we know that this is non-empty if and only if Q is isotropic over L. So this non-empty means there is an element here. That means, so there is a non-trivial solution for this. Because the 0, 0, 0, I think this is not n. This should be n minus 1. Okay, so now we've taken an element in this solution set and a matrix in the orthogonal group of Q, then look at this P times X is again a solution for this equation. So it's again belongs to Q of L. So this gives an action on the linear algebraic group SOQ on the quadratic Q. Further, this action is transitive. So it means given two elements in the Q of L, there exists some P in the special orthogonal group such that Px equal to Y, the usual notion of transitive action. Okay, so now we want to generalize this thing. So let G be a connected linear algebraic group over a field K. So that means it's a subgroup of GLN satisfying some relations. Okay, so for example, the GLN or PGLN is a GLN mod the center, SOQ, which just now we have seen, SUH, where H is a Hermitian form. So like a quadratic form, you can talk about Hermitian form and the unitary group and special unitary group of that. So they're all connected linear algebraic groups. And a projective homogeneous space under G over K is a projective variety with action of G, which is transitive for all field extensions. Okay, so, of course, over K, this X may not have a point at all. So Xk may be empty. So we want this transitive action to be for all field extensions. So whenever there's a point, so then we can talk about this transitive action. So the quadratic Q is a projective homogeneous space under the special orthogonal group SOQ. That's what we have seen before in the previous slide. So that's an example. And if you rewrite this asymmetric once again, it says that take a quadratic form over number field. Let X be a projective homogeneous space under SOQ. Okay. And if it point for all places nu of K, then X of K is not empty. So that in other words, the a quadratic form is isotropic for K nu for all nu, then it's isotropic over K. So we're just putting in a different language. Okay, now there is another theorem of Albert, Brouwer, Hasse, and Noether, which so so for that we want to see what is this. Let K be a field and A is a central simple algebra over K, and by a theorem of Wedderburn, we know that A is isomorphic to M and D, where D is a division algebra. That means it has every non-zero element is invertible in D. Okay, the index of A is defined as the degree of D, which is the square root of dimension of D over K. And of course, first note that the dimension of D is a square. That can be checked easily. And you take the square root of that. So that's called the index. And given algebra A, so one would like to know what is the index of that. So to compute that, Albert, Brouwer, Hasse, and Noether proved the following thing. So take a central simple algebra over a number field K. Then the index of A is the LCM of indices of the A tensor K nu for all places nu of K. So for example, so if A is a, okay, so let me write, okay, suppose A is a division algebra. Let's say A equal to Mn, just D itself. There's no matrix factor. So if, okay, now if you want to check A is a division algebra or not, it's enough to check locally it's a division algebra. So because when A is a division algebra, the index is nothing but the degree of D, which is the dimension of A. So from that, we get that from this. So if we want to check where every non-zero element of A is a unit or not, it's enough to check locally every non-zero element is a unit or not. Okay, now if you rewrite this in the language of projective homogeneous spaces, so take a central simple algebra over a number field K and let G to be the PGLA. So that means GLA, that means all the invertible elements in A for every extension, field extension, and P is going modulo the center. And X a projective homogeneous space under G over K. Now, if X of K is not empty for all places nu of K, then X of K is not empty. Of course, to relate these two, one has to understand what are all projective homogeneous spaces under this group G, and how does that connect to the indices. So that's a big theory, so we'll not go into that right now. So this theorem immediately gives this corollary by knowing what are all projective homogeneous spaces under G. Okay, now more generally, we have the following theorem of order. Let K be a number field and G is any connected linear algebraic group. So in the previous case, so this is a PGLA and here it is SOQ. More generally, take any connected linear algebraic group over K and X a projective homogeneous space under G over K. And if X of KV is not empty for all places nu of K, then X of K is empty. So to check that this variety has a K point or not, it's enough to check locally. That means at all completions, there is a rational point or not. Of course, if X of KV is empty for some nu, then this will be empty automatically because X of K is contained in X of K nu. So if this is non-empty for all, then the theorem says that this is also non-empty. Okay, so now what do we do? So that is a classical theory, and now we want to see some where you can apply this kind of scenario anywhere else. So the theme of today's talk is to build analogies between number fields and function fields of periodic curves. And we focus on local goal principles for projective homogeneous spaces under connected linear algebraic groups. So we want to generalize this theorem of order to some other fields. Okay, so for that, so we need to understand some basic definitions. So what is the discrete valuations? So take a field. So a discrete valuation F is a map from the F star, that is non-zero elements of F to the Z, which satisfies these two. So the first is just the nu of AB is the sum of the valuations, and the nu of the sum of the A and B is the at least minimum of these two. So the examples, this is a discrete valuation on Q. And if K is a field, and look at the rational function field in one variable. So take the polynomial ring and take the field of fractions of that polynomial ring in one variable. and given take an irreducible PT. So this KT, the polynomial ring, behaves like the integers. So there, for every prime, we define this metric, p-adic metric. But now here, take any irreducible polynomial, and you can do what you did exactly for the p-adic norm. So write this, given any polynomial, write it as a pt power d times gt. So take the maximum power of this irreducible polynomial, which divides that, and define the valuation of this ft to be d. And if but any element here is f over g. So the valuation of f over g will be the valuation of f minus the valuation of g. So that gives a discrete valuation on f. Now take a field with discrete valuation, any field, and look at this R nu, the set of all those elements in f star where the valuation is greater than or equal to 0. So, and you add 0, and take MV to be all those elements where the valuation is strictly positive and add 0 to that. And then this is a local ring with maximal ideal M nu, and we take the quotient. This is a field because this is a maximal ideal, and this is called the residue field. So examples. So this is and the residue field of this is the finite field. We talked about that, and the residue field of this valuation is this field because this is an irreducible polynomial. So the ideal generated by that is a prime ideal, so it's maximal ideal here. So this is a field. So the residue field of is that. Okay, now completions. So as we did for the p-adic valuation or p-adic norm, so given a field with a discrete valuation, one can define the completion exactly as before. So given this discrete valuation, there is a norm associated to that or metric associated to that. And once you have metric, then you take the completion, taking the equivalence classes of Cauchy sequences with respect to suitable equivalence classes. And this is a field. And of course, this value, the discrete valuation on f extends to discrete valuation f nu. And we say this is complete if f is f nu. Okay, so what are the examples? So the completion of Q is that, and if you take this field KT and you take the discrete valuation given by T is a irreducible polynomial, right? So you take the valuation we defined before and take the completion. This is going to be the Laurent power series. So it looks like this. And again, we have the Ansell's lemma. So this gives a method to determine whether some variety has a rational point or not, using some information over the residue field. Of course, given a variety over f nu, we don't have a variety over k nu automatically. So we have to do some juggling of the coefficients and so on. So there is, given this variety over this, we attach some variety over this, and if this is non-empty, if and only if this is non-empty, and so on. So this gives a method to go from solving an equation here to solving an equation here. For example, the question of isotropy of quadratic forms over f nu can be reduced to a question of isotropy of quadratic forms over k nu. Okay, so because of this Ansell's lemma, so most of these questions where some polynomial has a polynomial equation has a non-trivial solution or not, it's easy to decide by going modulo the maximal ideal or power of maximal ideals, like we did over Z and going mod P. So that's why over these fields, I mean, it's easy to answer all those questions, but then we want to see whether globally we can do something. So take a field and take the set of all discrete valuations and the local global principle. So this question, so take a field f, and is there a local global principle for quadratic forms over f? I'm asking specific, but you can ask more generally for any variety. So that means if a quadratic form over f is isotropic over f nu for all nu, is Q isotropic over f? Now, if k is a number field, then the answer is yes. Of course, I have to put the real valuations also. Let's assume k is a totally imaginary number field. So this is the theorem of Asay-Minkowski. And of course, in general, the answer is no. We can't expect such thing for any arbitrary field. So what is the example? So take Qt. So rational function field is one variable over Q. And look at this polynomial. So what are the coefficients here? The coefficients are in this field f. So like t plus 8 is in this field. Of course, 2 is here, and t cube minus 113t is also here. So the coefficients are here, and the variables are x1, x2, x3, x4. So this is a quadratic form over f of dimension 4. So in 4 variables. Now one can show that Q is isotropic over f nu for all discrete valuations of f. Of course, it requires a little bit of work. Once again, we don't have to check for infinitely many. So there are some finitely many. we have to check, and the remaining is automatically true. And of course, one can check this isotropic over RT also, and of course over CT. But Q is not isotropic over F. So therefore, this local goal fails even for quadratic forms over such a nice field QT. Okay, so, but now this is over Q, but let's look at QP. So let K be a periodic field, that's a finite extension of QP. Let F be the function field of a curve over K, that is a finite extension of KT. So if you don't know what it is, just look at KT. So the same thing as QT. So QT, it failed there, but now look at this KT where K is a periodic. So like, for example, QPT. And then this is the theorem of Quadratic and Parmela and myself. So if you have quadratic form of F in at least 3 variables, so if Q is isotropic over F nu for all nu in omega F, so omega F is a set of all discrete valuations of F, then Q is isotropic. Okay, so of course at least 3 variables is required. If it's just 2, then this is false. We have a counterexample for that. And there's a corollary. Okay, again, this is a theorem Parmela and myself we proved in 2007 by different methods, but this method also gives the following thing. So if you take this such a field like QPT, so every quadratic form in at least 9 variables is isotropic. So how do you show this one? To show this one, so we use this theorem. So over F nu, it's enough to check every form in 9 variables is isotropic over F nu. And again, so F nu is a complete field with a residue field, is either local field or a global field of positive characteristic. So in both 2 cases, we know that every form in 5 variables is isotropic. And using Hensel's lemma, we show that every form in over F nu is, every form in 9 variables is isotropic over F nu. And by this theorem, we have this one. After that, yes, this is 2007, this is 2009, but as I said, this is proved by different methods in 2007. But in using this also follows this one. Okay, so we made the following conjecture after verifying for some groups. So take a connected linear algebraic group over the function field F of periodic curves and X a projective in a space under G over F. If X has a rational point over all discrete valuations, completions, then it has a rational point over F. So this is exactly similar to Hodder's theorem over number fields. So we made a conjecture for this function fields of periodic curves. And of course, the big evidence for that is this one, for quadratic form, that is for SOQ. So the SOQ, this is true, so we made this, and also for some split groups we checked, this is true, so we made this conjecture. And then immediately after that, 2010, so Surendranath and myself proved this for PGLA. So we proved that conjecture for PGLA. So if you take a central symbol algebra or the function field F of a periodic curve and take a projective in space, and this has a local global principle. Okay, so in particular, the above theorem asserts that, again, if A tensor Fe is not division for all discrete valuation, then A is not division. As I explained this for the number field, the same thing is true here. It just follows from this theorem. Okay, so after 5 years, the Wu, a student of mine at Emory, so the previous one was a student of mine at Hyderabad University. He's a student at Emory. So he proved for, so take a central simple algebra or a periodic function field of P with an involution sigma of first kind. Suppose that assume that P is not equal to 2. Yeah, I forgot to assume. Okay, here also we need to assume some P is co-prime to the degree of this, the index of A. And let H be an Hermitian form over A sigma. So it's like quadratic form, but now with values in A and, okay, it's not just a symmetric, but it's sigma skew symmetric. And take this SU, the special unitary groups. So one can define, as we did for quadratic forms, one can define this. And X a projective in space under G over F. So if X of F nu is not empty for all nu in omega F, then X of F is not empty. So that means we have this conjecture holds for SU of A sigma. So the conjecture of Quadratic Parmela and myself holds for this group SU A sigma H. Okay, so now in 2021, so Parmela and myself, we proved this. So in the previous paper of Wu, so he took the involution of first kind. And here we use this, he uses a theorem of Saltman, which says any such central simple algebra is either a quaternion algebra or tensor product of 2 quaternion algebras. So using that, he proves this theorem. But when you go to the involution of second kind, we don't have such kind of result. And so assume that the 2 times degree of A is coprime to P. And let H be an Hermitian form A sigma and take G to be UA sigma H. Here is because in notation of second kind, this itself is a connected in algebraic group, so we don't have to go to the special unitary. And you take a projective homogeneous space under G, and the conjecture holds for this group also. That means if X has a rational point over F nu for all discrete valuations, then it has a rational point. Okay, so as a corollary, you take a connected algebraic group over the function field of periodic curves of classical type. So there are some types AN, Bn, Cn, Dn, but for D4 you have to assume it's non-trilitarian. Suppose the prime P is good prime. So again, so like in the previous cases, so we avoided here P is coprime to here and so on. So like that, for every group has some finite many primes. So we want to avoid those things. And let X be a projective homogeneous space under G over F. So the conjecture holds. So the conjecture holds for all classical groups except D4 non-trilitarian and avoiding some P avoids some finitely many primes. Okay. So of course, still this conjecture is open for exceptional groups and D4 non-trilitarian and in the bad prime cases. So for example, if prime is 2, so we don't even know for quadratic forms. So if P is 2, we don't know whether for quadratic forms there is a local global principle like this. Okay, so in last 10 minutes or so, let me quickly give an idea of the proof. So we're not going to explain much here. But so if you start with the periodic field, and the residue field we call it kappa, and O is a ring of integers. So we said this is a complete DVR, right? Periodic field, so it has a ring associated to that. And the residue field is finite. Now we have a smooth projective geometrical integral curve over K with the function field F. So F is a function field of periodic curves. And of course, once it's a function field, we can assume it's a function field of smooth projective geometrically integral curve. That's not a big deal. But now, so from curves, we want to move to the schemes. So now on this ring spec, so on this scheme spec O, the spec of this ring, so it has only 2 points, namely the zero ideal and the maximal ideal. So then we can get a 2-dimensional regular proper scheme, which is a model of this. That means the function field, this is X is a 2-dimensional regular proper integral scheme. The field of fractions of this is F. So that's why we call the model of X. And as I said, this has 2 points. So the 0 and the maximal ideal. So if you take the fiber over the maximal ideal, so that's called the special fiber, and the fiber over the 0, you get this X.
Existence of this kind of proper models is kind of non-trivial, right?
Yeah, it's very highly non-trivial. We use the resolution of singularities of Abyankar and Lippmann and so on.
Okay.
And so given a point of this X naught, so the X naught is a curve over the residue field. So given a point, so it could be a generic point. So this may not be a reducible curve, so it could be, you can have finitely many generic points or a closed point. But whatever it is, you take the local ring at that point and take the completion of the local ring at that point. And let Fx denote the field of fractions. Okay. Now here, this Fx, if X is a generic point, Fx is nothing but a complete discrete valued field. But if X is a closed point, so this is not a complete discrete valued field, and this is a 2-dimensional regular local ring, and this is a field of fractions. So here we don't have much, like Ensel's lemma, we don't have things like that. So there is a theorem of Arbeiter-Hartmann-Raschen using patching techniques. So if you take a connected linear algebraic group over F, which is F rational, that means the function field is a purely tangential extension. And let X be a projective homogeneous space under G over F. And so there is a local global principle with respect to these overfields. X of F nu is not empty for all X in X naught, then X of F is not empty. Of course, this should be good enough, but we don't know how to prove this X of F, how to decide if X of F nu is not empty or not. This should be X. If X is a closed point, if X is a generic point, this is a discrete valuation, we are happy. But if X is a closed point, so we don't know how to do this, how to decide this one. So that is the reason we want to move this to the only discrete valuations. So the method of proof is, so for any X corresponding to an irreducible component of, so Fx is a complete discrete valued field, so there we don't have to do anything. For a closed point, so this is a 2-dimensional regular local ring, and this is a field of fractions of that. So hence one reduces the problem to the field of fractions of complete 2-dimensional regular local ring. So far we are dealing with algebraic geometry, arithmetic geometry, now we are coming to the commutative algebra. because this conference is 2 parts, right? So this is a commutative algebra. So we have 2-dimensional regular local ring, complete, and field of fractions, and we want to study the structures over that. And here, in our case, the residue field is a finite field. So therefore, this ring is very nice. So one studies the structure of central simple algebras with involutions over such fields, and we classify what are all central simple algebras with involution of second kind. And we see how they look. In fact, they're all cyclic algebras, and some we prove, and then from that we conclude our theorem. So we use the following techniques from Galois homology, arithmetic geometry, and Milnor K theory. So I don't think if I give more details, it becomes too technical. But let me do one more thing. Try this one. Is there a non-trivial solution to this equation? I forgot to put the 0 here. So does this quadratic form isotropic? Okay, what are these numbers? I just randomly choose. They're all primes. Okay, so we're interested over Q, but now by Hasse-Minkowski, or just Minkowski because just over Q, it's enough to check over reals and QP. Over reals, this is obviously isotropic because it's a negative number. There's a negative sign, right? So there's a positive sign and negative sign, so you can always find. So this divided over this is a square. So positive number some square, so from that. But over QPs, so if P is not equal to 2 or any of these primes, then just some generality that this is isotropic or such QP, where P is not equal to 2 or any of these 4 primes. But if Q is 2, then you have to see why this is isotropic. And if Q is any of these primes, again, if this is a prime, if you look at this prime, then you look at this form itself is isotropic over Q 4639 because it's formed in 3 variables and all these coefficients are not divisible by this prime number. So you go modulo this prime number, then all these 3 are non-zero numbers mod this prime. So we have form in 3 variables over a finite field. So form in 3 variables over a finite field is always isotropic. So therefore this is isotropic. So you can like that for every prime it's true. So it's isotropic over QP and for all P and isotropic over reals. But of course you need to check over 2. That's requires some work. So that's the exercise you want to do this. And then by Hasse-Minkowski, this is isotropic work. So if anybody interested in doing some computer things, so try to find a solution for this one. Thank you.
Thank you.
Hello.
Hello?
You hear me?
Yeah.
Yeah. So, are there any questions that you want to have?
So, if you go to exceptional groups, the techniques will become very different, is it?
Yeah, completely different because I mean they don't come from algebra. Of course, G2 is okay because it comes from
Kelly algebra.
And F4 also one can try, but the other things are more difficult.
So these techniques have to be completely changed because you have to have some uniform techniques for algebraic groups.
Right. Yeah. We need uniform. Yeah, if you want to cover exceptional group, we need a uniform proof.
There are no further questions. We can thank the speaker again. Talk is going to begin in 10 minutes, right? 10.
అంది కింద పెడతావా నువ్వు ఎప్పుడు వేస్తావో ఇచ్చేయాలి కదా. సరే ఏం కావాలి.
Manish Kumar, the Bangalore Center of the Indian Statistical Institute, and he's going to talk about embedding problems for fundamental groups. Manish.
So maybe I'll begin by thanking Suratna and the other organizers and others for inviting me to give this talk and for the hospitality. I think our stay has been wonderful. All the guests were already very happy and so I think in this talk I'll try to introduce some questions which I think is interesting. Yeah. So and how do you decide the question is interesting? So one way is to see whether the question is fundamental or not, and other way is to make sure to guess whether it would lead to good mathematics or not. Yeah. So maybe I'll start with some fundamental question which is well known, and maybe it's a good warm up. Yeah, so let Q be rationals. Yeah, field of rationals. So anyone who has seen Galois theory would know this question. So what one can do is look at all field extensions of Q. Yeah. So L over Q is some Galois extension, and look at this Galois group. Yeah. So this. So one needs one fundamental question in Galois theory or number theory, if you like, is what Galois groups can occur this way. So the conjecture or the inverse Galois problem says that every group can occur this way. Yeah, every finite group can be realized as Galois group or some Galois extension. So there is a related group. Out of these group, one can manufacture another group, which involves infinite Galois theory. So what you can do is if you vary these guys, then these field extensions L over Q Galois, and take the so you get some groups, and there are some you get inverse system of groups, what is called an inverse system of groups, and you take the inverse limit, and what you get is a profinite group. Yeah, which is denoted by GQ. So it's called it is the absolute Galois group of so every finite the initial groups I was talking about, the Galois group of L over Q, they are all quotients of finite quotients of Q. Yeah? So another way to phrase this inverse Galois problem is to say that the conjecture is that every finite group occurs as a quotient of G. Okay? So of course this this is certainly a fundamental question. Whether so by the way, it's an open question. It's a fundamental question. So because this is something which you would want to answer as soon as you learn some Galois theory. Right? So in that sense, it's an interesting question. Another question is people want to understand GQ itself. Yeah. So what is GQ? What is the group, this profinite group GQ? So, well, if that is an interesting question, this is an interesting question, but one can argue that this is not a fair question. Yeah. So, how do you describe what this group is, GQ? So it's not. No one expects a reasonable answer to this question. Yeah? So you can't give certain elements and relations between them and so on, generators and. So that kind of answer you can't give for more or less any profinite group. Yeah. So profinite groups, unless it's a very special kind of profinite groups, such description is not possible. So it's a good question, but it's not a fair question. And so what people do is try to derive. So basically the idea is to understand GQ. So one derives some questions out of it, like what are all finite quotients. One can go into some representation theory and some other related problems, like embedding problems kind of question one can ask, yeah, for DQS. So in the same spirit, I'll try to ask questions which are not unfair, yeah, like this, but maybe we want to understand something, but we'll frame some questions which are somewhat reasonable and one can try to answer it. So the next, let me now get to the topic of our interest. So let C be a smooth curve over an algebraic groups. So if you like, over complex numbers, or any other, but I'll be interested in characteristic P later on. So maybe complex number is not a good idea, but to start with, let's close. Okay, so K is same as K bar. That is what I want to say. So when you have a smooth connected, because we want to talk about something called fundamental. Yeah. So when you have this smooth connected curve, then first thing what you can do is you can associate a field to it. Yeah. So Kc is the function field and over of C. And as soon as you have this function field, of course you can do you can play the same game. Yeah. So you can ask what are the Galva extensions, but I don't want to look at all Galva. So one can ask all the what is this absolute value? I mean, one can ask this question, yeah. But this I don't want to ask. This has an easier answer. That is why I don't want to ask. But maybe by the end of the talk, someone can guess what this is. But what I want to know is, so I want to put some more restriction on the field extension. Yeah. So maybe I'll. So there are other ways of defining this, but for me, this Ital fundamental group of C. So usually there is a base point, etc. So I don't. If you, as we know from topology, whenever you want to define a fundamental group, there should be a base point. So I'm sort of putting that under the reg, and I want to think of things in terms of Galva theory. Yeah, and actually it's not unfair because this is how it came about. Yeah, so this is pre-Grothendieck is how this is how it came about. Then post-Grothendieck things became more precise, as Nitin said, and well, one can say it became more understandable, but it also becomes more difficult to explain it in a more elementary form. But this is a more elementary way of explaining it. Yeah. So what you do is consider inverse limit of Galva group of L over Kc. Now the inverse limit is over all Galva extension such that so we want I'll do some operation. So I mean, if you don't know that much algebraic geometry, I'm just saying that for students, yeah, then don't worry about it. But if you know, then you consider the normalization of C in L, yeah. So that will give you another curve, yeah. So it gives you another curve, and there is a map to C. So this is also a smooth curve, by the way. And because we are in curve case, normal is same as smooth. And this should be unramified or Ital. Ital is same as unramified in dimension one. Yeah. Okay, so and unramified basically means that this is a map. Yeah. So what it means is that over every point there are same number of points. Okay, so that is all it means. So sometimes it may happen that over some point you have only fewer points. Yeah? The pre-image becomes smaller. So that doesn't happen unramified. So this is the description of fundamental group in terms of a simple Galois theory, not too difficult to understand. Meaning understand the definition. But the group is not so easy to understand if you are in positive character. Yeah. So objective is to so question maybe. So this is maybe unfair question. What is phi 1 eta? See, unfair in the sense of this. What is G? Yeah. So saying what is this?
What are the properties you're going to study?
I'll come up with. Yeah. So it will be more finite quotients and so on. Yeah. So those kind of properties, not representation. So you'll see. So GQ is just for analogy. We'll just study this object. Yeah. So what is phi 1 eta C? So though I said it's an unfair question, if the base field K is complex numbers, this is not unfair. It's actually, it was known a long time ago, let's say, maybe to Riemann or something. So if K is C, so maybe I can attribute it to Riemann. I don't know whom exactly I should attribute it, because the groups were not defined, but I mean, in principle, Riemann knew about it. Yeah. So if K is C, then phi 1 eta C is so then C, remember, is a topological object. It's a two-dimensional guy, and it's a Riemann surface minus a few, not necessarily compact. Yeah. So it's a compact Riemann surface minus a few points possibly. Yeah. So then you can compute its topological fundamental. Because you are over complex numbers, so it's not going to be equal. There is an operation called profinite completion. So what you do is look at all finite quotients of this topological fundamental group. That forms an inverse system, yeah? And you take the inverse limit of that. So that is what this profinite completion is. So this is not too bad. Basically, Riemann proved what is called a Riemann existence theorem. So whenever you have a morphism of whenever you have a covering of Riemann surfaces, then Riemann existence theorem says that these are actually algebraic curves, and the map is an algebraic map. Yeah, so it's going to be a finite map. So from that, this more or less follows. So, and of course, this is a nice group. Yeah, phi 1 topological C. We know that if C is affine, this is phi 1 top. C is a free group generated by 2 times genus of so you have to compactify it. So let me denote by this plus r minus 1 points elements. Free group generated by these many elements, where r is number of elements in C bar minus. So you take the smooth compactification C bar and look at the points you are missing. So if you are not missing any point, then C is not affine. And then also we know what the description is. Yeah. So if C is projective or proper, they're same in this case, lowercase. Then so I don't want to tell you the description completely, but it's called then it is it's called the surface. So it's generated by basically phi t. So it's basically generated by 2G elements modulo a relation. Yeah. So if you have seen, you know it. Or if you have not seen, don't worry about it. So this is the characteristic zero picture, and so very smart gentleman asked a nice question. Nice question in characteristic T, motivated by this thing. Yeah. So, is it in the middle? Yeah. It's in the middle. Yeah. Yeah. Maybe I can bring it close. So as I said, so this was this is now a theorem. So I'll write it as a theorem, but it was conjectured by Bianca. So what he said is that it's conjectured for affine. Yeah. So K equals characteristic K equals P. So we are in the suburb setup, but now we assume that the characteristic is positive, P greater than 0. Then the question is, so from here, what we can deduce is that the finite quotients of this guy, phi 1 eta C, is generated by 2G plus R minus 1 elements, if C is affine. Yeah. So he said that something similar should happen in characteristic T as well. So G is a quotient of finite group G. So if I don't mention, just assume, yeah, finite group G is a quotient of phi 1 C, if and only so C affine. So I'm not going to talk about this, but the question is, yeah, so maybe I'll make something on. So G is a quotient of phi 1 C if and only G mod. So you consider the subgroup generated by all P zero subgroup. Yeah, so that is that will be a normal subgroup. Okay, so that subgroup is denoted by P. So all P zero sub, this P is same as that. So you mod it out by a subgroup generated by P zero subgroup. So this becomes a prime to P group. Yeah, so the order is prime to. So if and only this is generated by 2G plus R minus 1. So yeah, of course. So it's motivated by this question. So it's not only over C, but the statement is true for characteristic zero. That is what your question was. Other non-complex, but algebraically close. Otherwise, there are obvious reason. Absolute Galois group of the base field is not.
But here also algebraic.
Yeah. So I'm always talking about algebraic. C is a curve over algebraic. So this was so maybe so this is a fair question in the sense we are not asking about the whole group, but only finite quotients of it. Yeah, and this also led to a lot of wonderful mathematics. So his intuition was on topology. Yeah, and but if you look at the question, it doesn't involve any topology, right? I mean, you can't really imagine thinking about this problem topologically because it's all algebraic curve. There is no way to think about it topologically. No assumption. So it will. I mean, this conjecture will holds means while ramifications are allowed. Yeah. So everything, all possible covers are. So as you can see, the statement doesn't involve topology, but of course the intuition is topology, right? So the first advancement was so there was another I guess very smart guy who actually built the bridge from here to topology and answered it using topology. Part of the question. Yeah? So one direction. So the forward direction of this thing is due to Grothendieck. So what he did was he answered this question. Let's say he connected it to a curve over complex numbers, let's say. Yeah. So I can't in the given time I can't explain his work and talk about what I want to talk. But the point is, it led to very nice mathematics. This was so when Grothendieck came, he sort of introduced a lot of language. Yeah, and mathematicians are very careful about what to read and what not to read. So only if you sort of solve some big problems, then only they venture into it. So this was one of the initial success stories of. So he had many successful stories, but this was one of the initial ones. So he proved this thing and he built the bridge. So the bridge is more important than the theorem, yeah. So he built the bridge, and that's why people thought, okay, this is a good machinery, and it also made things more precise. So this forward direction was done by Grothendieck. For the reverse direction, so there are many people who tried. So this was done in late 60s. So the conjecture was in late 50s. This direction was done in late 60s, and the other direction was more like a inverse Galois problem kind of thing for this thing. So this took a long time, but so there were many people. So Sayre did it when the curve is a fine line and the Galois and the groups are assumed to be solvable. Yeah, then he showed that you can show that there are if G mod PG is trivial in this case, because you're in the affine line case, that genus is 0 and the 1 point missing. So the G mod PG is trivial, then you can realize, so that means G is equal to P. And such groups are called quasi P. Yeah. So you show that every quasi group P groups, you can realize it as a cover of P. If G is solvable. And then Raynaud, so they all build up on each other's work. Yeah? So Raynaud built up on Sayre's work and proved that this is true for affine line, yeah, for all quasi. And then came Harbater, who used Raynaud's result and proved it for arbitrary curves, for all affine curves, smoother ones. Yeah. So this is the story. So of course, I mean that sort of answers the question at the level of inverse Galois problem kind of question. Yeah, but it doesn't answer. So knowing finite quotients of phi 1 etal C doesn't tell you what phi 1 etal C is. So for a profinite group, this will be true if the group is what is called topologically finitely generated. So it's a topological group. If you can find a finitely many elements such that the group generated by it and take the closure happens to be the whole group, then if you know all the finite quotients, then you know the group. But this is not true for affine curves. It's not topologically finite. It's actually very big. Yeah. So the rank is same as the cardinality of the piece. So it could be very big. And so maybe I'll say something about projective curves just involved. So if C is projective, then this group phi 1 etal C happens to be a finitely generated group. Finite rank topology. It's not fine. It will never be finitely generated, but finitely generated in the topological sense. So it happens to be a finitely generated group, but we don't know what the finite quotients are. So that's another interesting question. So there is not even a conjecture. So here at least there is a conjecture. There was a conjecture by Argenter. When C is projective, there is not even a conjecture on what all the finite quotients are. So for prime to P, it is okay. Yeah? So away from P, this more or less behaves like this. Yeah. So Grothendieck's result applies even in the projective case for prime to P part, but the P part is not. But there is a mix of things. Yeah. So now, so once you know all the finite quotient, then see the inverse limit consists of two things. Yeah, inverse system consists of two things. There is this all finite quotients of the group, And then there is if you remember inverse system, it also has maps between these groups. Yeah. So another way is to understand this group is not only understand the finite quotient, but also what maps appear in it. Yeah. So that is encoded in this. So I'll just check if I haven't forgotten something. Yeah. So I think this. So this is encoded in something called embedding problem. Yeah. So let me just see what an embedding problem is. Definition. So let yeah, so maybe I'll not write it as much in words. So say you have a sequence of finite groups, gamma surjects onto G, and the kernel is H. Yeah. And suppose you have a surjection onto G. So to say that this morphism, let's call it beta, yeah, and let's call this alpha. So to say that this map beta is in the inverse system, it's enough to say that there is a surjection from this to gamma. Yeah. So if you have a surjection from this to gamma, that means that this map is also in the inverse system, right? So this is called an embedding problem. So the embedding problem consists of a surjection from gamma to G and a surjection from the fundamental group to G. Yeah, two surjections. H is the kernel, yeah, so which you can manufacture out of it. And the question is when. So does there exist gamma? So you say that this embedding problem has a solution. So maybe I'll write it this way. So gamma is a solution if gamma composed gamma followed by beta equals alpha, and maybe gamma is surjective. So if you suppress gamma is surjective, then this is always true. Okay, so you can always find a gamma such that the diagram commutes, but that may be is a small lemma. So it depends upon cohomology dimension of C. Yeah, so cohomology dimension of this affine curve happens to be less equal 1. So for that reason, you can always find a gamma such that this diagram commutes, but surjectivity is something non-trivial. So if you translate in terms of Galois theory, what you are saying is that if you are given so if you are given this cover, so alpha leads, so if you are given this epimorphism, this leads to a cover. Yeah. So maybe X to C, a G Galois cover. Yeah. So you get a G Galois cover, and if you want to think in terms of field theory, it's a field extension with Galois group G. Yeah. So this is what the picture is. Yeah. So this is what is given, and you have a surjection from gamma to T, and finding a solution means want Y. So I'll draw it here. So you want a Y and a cover of C. So this is Italia, because it's a projection from the Italian fundamental. So the morphism is Italian. So want Y is such that the Galois group here is gamma, and again this cover is Ital, and plus the diagram commutes means it should factor through. It should factor through this. So there is a so this map Y to C is same as there exists a map Y to X followed by X to C, and finite morphism and this diagram. Or in terms of field theory, there exists a field extension KY of KC, which is gamma, and we want this KX to be contained in KY. So that is so maybe that is the reason. So maybe Galois theory people were studying this, so that's why they called it embedding problem as opposed to lifting problem or something. So if geometers were studying it earlier, it would be called lifting problem, but I don't know, some different thing. Okay. So So see, the point is you can simplify the situation a little bit. So we know that, as I said, we always have this solution. We always have a map gamma such that this diagram commute. It may not be surjective, but we always. So what you can do is replace this by another thing. Image gamma is, let's say, gamma naught. So that's a subgroup of gamma, and then you can try to convince yourself that so you'll have so this gives you a solution, the surjection to gamma naught, because that is the image, and you can make a semi-direct product of gamma with H, because H is a, so there is an action of any subgroup of gamma will also act on H by conjugation. H is a normal subgroup. So you can make the semi-direct product, and the kernel is this, and this surjects onto gamma. So there is a, so gamma naught is a subgroup of gamma, H is a subgroup of gamma, and they together generate gamma. So that's why there is a surjection here, and so this is related to the earlier embedding problem in this way. Sorry, I should really write 1, not 0. Yeah, so so if we get a surjection here, then of course I can compose it with this and get a solution, yeah, to the original embedding problem. So the upshot of all this is that we can assume that this is a split embedding problem. Yeah. So there is a splitting in this case, and hence we can always reduce to split embedding problem. Yeah. So solving this embedding problem will give us better understanding of the Algebra group. So I hope I've convinced you of this this thing. Yeah? So if we solve these thing, then we'll get a better. So actually, after Arbiter, Pop did some more work and proved something stronger than what Arbiter had proved. So what he said was every. So maybe this is Pop's result. So every quasi-P embedding problem has many solutions. So I mean, has a solution, but in fact, cardinal decay solutions. So any quasi-P embedding problem for any affine curve, a fundamental group of affine curve has number of K solutions. So by quasi-P embedding problem, I mean that the kernel is quasi-P. Okay. So what he proved was that when H is a quasi-P group, then you can always solve this embedding problem. Yeah. So so it's not too bad from here to see that this implies Nagata conjecture. So this is a stronger result. So just check if this is all right. Yeah, looks okay, right? So in fact, what you so one can reduce the problem further, because because of Pop result, we don't have to worry about when H is quasi-P. Yeah. So this side. Yeah. Sorry, I missed the word quasi-P. Quasi-P means the group generated by all P0 subgroup of so T mod PG. So H mod PH is identical. Yeah, H is generated by all P0 subgroup. That is what was. Thanks. Yeah, so one can simplify this further. So what you can do is consider H mod PH. Yeah. So if you are in the arbitrary setup when H is not quasi-P, then PH is a normal subgroup. It will be so if H is normal, PH is also normal in gamma. Then PH is also normal in gamma. Okay, it's called characteristic group or something. Yeah. So but you can see it directly. Yeah? So it's actually if H is normal subgroup, then PH is normal in gamma. So you can quotient it out by this. So you started with this exact sequence. You can quotient it out by PH, and this remains the same. So the embedding problem you started with, you can split it into two parts. One is this. So here, now this group is prime to P. Yeah. So such embedding problems are called prime to P embedding problems. So if the kernel is quasi P, you say quasi P embedding problem. Kernel is prime to P, you say prime to P embedding problem. So say you can solve this embedding problem. So this is the difficult part. Then then we can use Pop's result, and so you form another sequence. So if you can solve this embedding problem, means you'll have a surjection from this to this. Put gamma here and PH here, and and then use Pop's result to complete this solution for the original embedding problem. Yeah. So one can also assume that H is prime to P. Yeah. So the good thing about prime to P groups is things are more well behaved. Yeah. People understand. So as I said in the beginning here, prime to P, there is not much of an issue. Yeah, people understand it. P is very similar to what happens in characteristic zero. So it becomes a slightly more reasonable problem. Answer. Yeah. So the general question is. So this is the question I want to advertise. When is such an embedding problem, and when does such an embedding problem have a solution? So I'm going to have C, gamma, H, and with radius reduction, you can also assume it's split, and H prime. In fact, one could also ask how many solutions does such an embedding problem have. So earlier, if this is not if H was not prime to B, then it would have infinitely many solutions. So there is no question about quantifying it. But with this, I'll convince you that there are only finitely many possibilities for such an embedding problem. Yeah. So it could be zero. That means it's not possible to solve this embedding problem. But even if it is possible, there can't be too many. Yeah, it's going to be finite.
So with the splitting, I mean the translation to geometry will mean white weights as a section or something.
No, splitting just means so it's some group theoretic condition. It doesn't mean.
It doesn't have a geometric translation.
No. Yeah, I don't think there is a geometric translation. It's just it's Galois theoretic. So somehow, yeah. So one can do some Galois theoretic explanation, but not really a geometric. One can interpret it in some Galois theoretic. So basically, this is a subgroup. So you sort of quotient it out and. So let me try to give you some reason why some of these embedding problems may not have a solution. So there is some topological reason why some of them will not have a solution. No, I'll tell you some obstructions, some reasonable obstruction on why. So some topological reason why some of them will not have a solution. So they are all consequence of Abdenter's tendency. So let's try to understand in terms of covers. I mean group theory nobody understands. Yeah? So we only understand geometry. So let's try to understand what it means in terms of covers. Right. So you have C, you have a G cover X. Yeah. So if it has a solution gamma, then my geometric translation tells me that I can find an etal cover y to x, yeah, such that the whole group is gamma. Yeah, so this group is gamma, this is G, and this is H. That's the picture. So that tells you that H is a quotient of etal fundamental group of X. Yeah. So that already gives you some condition, and H is a prime to P group. So that case, even Grothendieck knew. So before now, you don't even need the reverse direction. Just the forward direction is good. Yeah. So you see that what it means is that so maybe let me call this this star. Yeah. So this is what I'll refer to. So star has a solution, implies H is generated by 2 times genus of X bar. So you pass to the smooth compactification plus, let's call it Rx minus 1, whereas again, you know what Rx is, yeah? Rx is the number of elements in X bar minus X. So just from this theorem, you can conclude this. So I mean, then you know how to construct many examples. So this is one obstruction. You can see there.
Suppose you assume H is a quotient of 5. Then does it have
So there are more of. So I don't know. I don't think it is true. So it is not true, but so this is certainly necessary, but it won't be sufficient, I think. So one not sufficient. Yeah. So there are some other issues. Yeah. So maybe, I don't want to talk more about this thing, but I want to say when maybe you can solve it. Yeah. So I'll give you some necessary conditions on when you can solve it. But yeah. So I mean this. So as this is a problem which is a little more difficult for me to handle. Yeah. So I'll change the problem a little bit. Yeah. So it's like and try to answer that. So it's like you know, if you lose something, so there's this joke, right? If you lose something, then you don't. Sometimes you search somewhere else because that's where the light is. Yeah. So in that spirit, what I'll do is I'll change the question a little bit and try to see answer those kind of. Yeah. So it's related. It's not too far off. I can argue that it's the same spirit. It's the exact same question, but maybe some other question. So you can't necessarily answer whether this embedding problem has a solution or not. But you can ask whether if I take some subgroup of pi1 etal C and assume that this embedding problem restrict to that subgroup, meaning the image of, so this is alpha. So alpha of that subgroup is holomorphic. Then whether the embedding problem is solvable for that subgroup or not. Yeah. So I'll answer those kind of questions. Yeah? And you know, I'll consider only finite index of. I'm interested. So we are doing geometry. Yeah. So we don't want to take arbitrary subgroup. We want to take finite index subgroup, and that will correspond to some cover of C. Yeah. So what I'm trying to do is not solve the embedding problem for pi1 etal of C, but some etal cover of C and look at pi1 of that. Yeah. So that is the translation. So let me just define. So maybe definition and phrase the question in this. So sorry. How much time do I have? Yeah, 15. So hopefully there is something about this problem. Because it's a solution to this embedding problem. So you have a projection from here to gamma. So that tells you that so as anytime you have a suggestion to this, you look at the kernel of this thing, yeah, and quotient so the Galois theory tells you that you can find a Galois extension of KC such that the Galois group is gamma and that is because so and that by definition would be so that is what it is this clear? I just thought. So so let phi is some subgroup. I mean, one can define more generally, but just think of it as finite index and a closed subgroup as well. So I mean, so it's not finitely generated topological group. So one should assume. So all groups are, if you think in profinite group, all groups you should consider is some closed group or open groups. So closed and open are same thing if it is finite. Such that so say pi is some subgroup of this such that pi alpha of pi. So I'll define something with respect to this embedding problem. Yeah. So alpha of pi is G. Then we say that then say embedding problem restricts to pi. I mean, if it is not D, then you can't even talk about solving the embedding problem. So this is needed. And what it means basically is you are looking at a curve which is sort of linearly disjoint from this. So the field extension you get out of this curve is linearly disjoint from the given curve, which comes out of it. We say pi is effective if, moreover, so apart from this, it restricts. We want embedding problem as a embedding problem restricted to pi. So such a subgroup we call is effective. So now you can transform the question to ask which subgroups of pi1 etal C are effective. Which finite index closed subgroup of pi1 etal C is effective subgroup. Yeah. So before I go into this, maybe some small observation will tell you that there is some relation between these effective subgroups. So if you take this maybe if you got some intuition out of it, then you can see that if you take a subgroup of an effective subgroup, that should also be more or less effective. Yeah, bearing some cases. So what is the reason? So the exact statement is that if pi is effective for the embedding problem star, then and pi 0 is some subgroup of pi, again finite index subgroup, such that so maybe finite index etc. may not be either, but that is how I think about such that embedding problem restricts to pi 0. So of course, if you take a subgroup, you want to say pi naught is also effective. So first of all, it should restrict. So that hypothesis you have to put in activation, so this is necessary, of course, to being effective. And say the size of it, and then more or less for most such it will happen. Yeah, but to put it completely precisely, if the index of pi naught in pi is co-prime to the order of h, then pi naught is effective for so then pi naught is also effective. So this is not very deep. This is just doing some basic level. Yeah. So just wanted to say that once you produce one, there are many candidates. Yeah. So okay. So now I'll just maybe mention some results. So one is maybe one is due to Halbert and Stevenson. So they were trying to they proved something which basically in this language means that certain subgroups are effective. So, theorem of Stevenson. So yeah. So let C from Z to C be an Ital cover. So I want to give you some subgroups of phi1 Ital C. Yeah. So the best way to take a cover and look at Ital cover and look at phi1 of that. Yes, so phi1. I'll say that phi1 Z is going to be effective under some hypothesis, such that C from so you take the fiber product over C and take the normalized fiber product and assume that this is so this will be Ital. Normalized fiber product will be actually this is you don't have to do normalization. I'm restricting it to a fine set. So just the fiber product will be Ital. Yeah. So, but it may not be connected. So, what we pose is that the C is connected. So, let's give this a name. So, call it X. It's base change of this map to X. So, XZ is so actually let's consider. So, it's in terms of this thing. So it's in terms of the completion. So compactification. So get the map C from X D bar. So it passes the completion, smooth completion. So this is unramified. So I'm also assuming that this is connected. So connected. First assumption is this is connected, and then this is unramified over so something called the relative rank, which is less than the rank of it. Yeah. So if you like, you just assume rank of H. But it's ramified over rank of H number of points. Number of points of Z bar minus. So see outside Z, so over Z it's already unramified. X is that thing. So I'm working for this embedding problem. So X is this thing. So whenever you are given an embedding problem, you have this problem. So so this will be ramified. So if you extend this map, then it may be so it may not be ramified on all the boundary points. Yeah, so it may be ramified at certain number of boundary points, maybe not ramified at certain. So you assume that there are at least relative rank of H in gamma, number of points in Z bar minus Z, where this map is unramified. Then the conclusion is then phi1 Z is effective.
Connectedness assumption is like disjointness.
Yeah. Yeah, connected just means yeah. So it restricts. Disjoint.
Gamma group and
yeah.
gamma group are different.
Yeah. The field extensions are linearly different. So yeah, that is precise. So then that is needed to say it restricts, and then this is needed to sort of work through it. Yeah. So this is So and then they also produce some examples, yeah, of this thing such that cover such that this happens. This hypothesis is satisfied, but they have to go through a large index subgroup and so on. So the index somehow becomes very big, but it's possible. Yeah. So so later on, so this is maybe this will be the last time we do this. So this better. So this last thing is that, so under some hypothesis, I can find an index P subgroup, and those hypotheses are more numerical in nature. Yeah, so it's something on the genus and so on. So maybe I don't know. So what time is it? 7. So. Yeah, so maybe if time permits, I'll tell you what relative language. That's not too bad, but let me just state the theorem. So there is a statement in higher genus as well, but it's somewhat neater in the affine language. So I'll restrict to this. Yeah. So one can always show that there are many effective subgroups, but I want to. For any embedding problem, there are effective subgroups. That's not too difficult, and you can make sure that those effective subgroups are index P. So that's not too difficult. But I want to characterize it in terms of some discrete invariants, not just some existence kind of theorem. Yeah. So let's say T to T is a p-cyclic cover such that genus of Z bar is greater than twice the. So you don't need twice. Basically, you want that yeah. So this surface group of that subjects onto some relative generating set of X. But if you assume this is going to be good enough. Twice the relative rank of X in gamma, plus one more condition, which basically is a condition on the rank. So if you have such a cover, then it has wide ramification at infinity. And so when you have a wide ramification and at infinity, there is something called the conductor, yeah, which is some number. Let's call it R, yeah. So that number determines in fact the genus in this case, yeah. So genus is going to be P minus 1 times R minus 1 over 2. So that now, so you want that number R to be different from. So there is another cover here, right? Yeah, this. Thankfully, I haven't erased this. So this cover is given. So this also is A1. So this cover also has some upper jumps in the ramification at infinity. So you want that R to be different from all these jumps. So this will be true if you take genus to be very high. Then this will always be. Yeah, so that technical, so plus one more condition. So let me just, that condition is satisfied if you take genus to be bigger than some number which is determined from this cover. Yeah, from this embedding problem. Fairly concrete. Then phi one set is. So then, but I don't know how many. So there is one solution. Yeah, but I told you want to quantify as well how many solutions. Yeah. So that I don't know. But you can see there are only finitely many solutions. Right. So that maybe I have some picture. Yeah. So here. So H is a prime to P group. Yeah. So if you have such an embedding problem, a solution to an embedding problem, this picture will be there. Yeah. So that means there should be a surjection from. So H should be a quotient of pi1 etal of X, and H is a prime to P group. So there can't be too many such surjections. Yeah. So that means there should be a surjective map from pi1 topological of X to H, and that is only finitely. Yeah. So there can be only finitely many solutions to this embedding problem. So I can so I could say a little bit more about the proof, which will tell you that this question should lead to some interesting mathematics. Yeah. So that's to make the justification that this is an interesting question. So the way this proof goes is so you are given this cover, yeah, X to G. So I'll just say in words rather than write. So you are given this cover X to G, of course. What you do is sort of find a degeneration of this cover of G cover. So all the members of that cover is going to have a gamma group G, but it degenerates into. So this curve should degenerate into some other curve which has some reducible component, and then the top thing will also basically have to be reducible if you do that, and such that on some component this cover is sort of trivial. So on some component the G will be non-trivial cover, and some other components this cover is sort of trivial in the sense that it's same is basically identity map taken G number of times. Yeah. So if that happens, then you can sort of use something called formal patching to construct new covers. Yeah. And if that component has high enough genus or so on, then you can use formal patching to cook up this cover. So there's only one way I could find the degeneration. Yeah. So when you sort of think of you embed C, so you think of C in some C cross A1. Yeah. So you consider C cross A1, and you blow up origin. So you get a line, projective line, and and then you sort of yeah. So it yeah. So if you consider this T equals 0 in that case, so there's this then it becomes a crossing. Yeah. So that's a degeneration of C in some sense. Yeah. So that's one degeneration which I know, and that's where one applies this methodology to get this result. But if one can find more and more degeneration, so it sort of reduces the problem to finding some degeneration. So, and that, of course, I think is quite interesting question in its own right. So it's sort of linked. So maybe I'll stop.
Thank you, Anish, for your presentation. Are there any questions, comments?
You already started with an embedding problem, that is X to C, and then you got a Y. Trying to find the Y.
Fine.
Now, are you actually solving it for the Z part of it? Are you solving the embedding problem?
It's not the original embedding. Yeah, so maybe I should have said something about it. So what I'm trying to do is I take a cover Z, yeah, which is an etal cover, and such that this thing is still so when you do the base change, it's still a connected cover. Yeah. And now I'm trying to solve the embedding problem for this.
That's what I'm asking.
Yeah, that is.
So in other words, if you do it for all Z, or somehow you carry on some descent data, and you actually solve the original problem by varying the Z's or some descent.
But there's
it's a descent data.
But there is obvious obstruction, as you can see. All the embedding problems you can't solve. Yeah. So if I give you H big enough, then
but even then, it's already taken.
For C, all the embedding problems, there are some restrictions. Yeah. But given any embedding problem, I can always find a Z. In fact, I can give you some criteria such that the embedding problem is solvable. So that kind of thing will not work.
There is some issue with the descent.
Yeah. So it's somewhat arithmetic in nature. So because you have to analyze all H covers and so on. So I have a student who is trying to work out some more to answer some more questions at this direction for me. So hopefully something. So some new results are there, but maybe she will when she gives some thoughts on this.
Is there any relation with my absolute dialog group of Q?
No, that is it was just an analogy. Yeah. So by the way, that question I had asked, can anyone take a guess what this group is? Say complex numbers and maybe move it now. So it's you are taking basically all possibly ramified curves. Yeah. So every embedding problem you can essentially solve. Yeah, because you are allowed all sorts of ramifications. So this group is actually a free group on so profinite completion of a free group on infinite linear system. So that's why this is not a too bad a question. And this is true even in characteristic P. So the proof is more or less similar. Yeah.
Case, so you change, keep varying the points.
Yeah. So there is no fixed ramification of this.
There are no further questions. Then thank the speaker again. So we're going to meet in 20. talk of the morning session today. We have Professor Krishna Hanumantu from Chennai Mathematical Institute, and he's going to talk about session. Krishna.
Thank you. So let me start by thanking the organizers. Has been mentioned already, it's been a wonderful conference, very nice hospitality. And thank you for inviting me. And let me also say that some of the audience members have heard me talk about these things before, so I apologize to them. Maybe there will be some new material or something. So today I want to talk about Seychelles constants. And as Manish said, there's some fundamental problems or questions in any area. So I'd like to, as I go along, connect this to some such questions, and maybe give today, just a survey of what are some important questions on that. People can convey that, but I will maybe see at the end I mention some new questions. Okay, so let me set up the basic notation. So I'll mostly stick to working on complex numbers, though many of the things are more general, but not all. And I don't want to worry about this. I'll stick to complex numbers because that's where most of the work is. And in fact, so the setup for this will be some non-singular projective variety. So I'll work with non-singular projective varieties. Let me try to give the definition in the beginning, and then we'll see some examples. So if you have an ample line bundle on X, the point of X, the Seychelles constant has two equivalent definitions. So we call this Seychelles constant of the line bundle at the point, and this is denoted by it. So if the variety also needs to be mentioned, we'll call it like this, but often we'll omit X from the notation. So this is, there are two ways of defining this. The first one is easier to write down and think about. We take the infimum of these ratios, L dot C divided by multiplicity, where we vary over all irreducible and reduced curves containing X. So we look at all curves that contain the point, and you take the ratio. So L dot C is the intersection number, and multiplicity is the multiplicity of the curve at that point. So this is a non-zero, non-negative integer, positive integer. It measures the singularity of the curve at that point. So it is 1 if the point is a simple point, and if and only if it's a simple point, and higher the multiplicity is, in some sense, more the singularity. Equivalently, we also have, okay, so once and for all, I will fix this notation. So this is the blow up at the point, and E is the exceptional device. So it's a simple calculation to see that this infimum is this supremum. You take this is because nef means this divisor is nef, means that it intersects all curves non-negatively. If it intersects all curves non-negatively for some particular t, you can write down what it means and translate it downstairs, and you will get some bound. If t satisfies this, then t will be, less than this. So one can check this. And because of the way the ample and nef cones work, this is also equal to the supremum, and we will occasionally use this. So this is the same as this equality. So the closure of the ample cone is the net cone. So this will be achieved wherever this is achieved is the Seychelles constant. And just until that point, it will remain, it will be actually ample. So this this came up in the work of Demai, who was inspired by a criteria for ampleness of Seychelles and who was motivated by a question of Fujita. I'll mention that in a minute, but he defined this and he was inspired by this, which I'll now write. So actually now when I write this, you will, in this modern language, we say that L is ample if and only if epsilon delta x. The Seychelles constants are all positive. Of course, I initially maybe one should start with the NF, otherwise. So if it's NF, then these are all non-negative integers. So we can talk about the infima, that is a non-negative real number. So this is the definition, and let me so he was looking at Fujita Conjecture. So what, before I mention what the conjecture is and how it is connected to Seychelles constants, let me just define the notion of generation by SJs. So I'll use yeah. Okay. So let me just quickly define this. This is the foundational thing for a non-negative integer. We say that L generates at some point x if you have the natural restriction map of sections so you say that this is the ideal sheaf of that point, the evaluation map at that point, so s plus first power of that point, ideal sheaf, is on. So for example, if s is 0, L is equivalent to L, I mean, it's globally generated or base point free at x. Of L. So that's what zero jets mean. So Demai was looking at this, and let me just repeat what calculations he has done. So how do we determine when does L generate S jets? So I want to understand this, and you will see that this can be translated to a question of cohomology vanishing once you go to the groups. So what is this? So this, let me write some implications. So this happens if, so there is a short exact sequence in the picture here, right? So you can look at you tensor that with L, and take the cohomology, this vanishes. This is onto if H1 of the next term. So this is L tensor. So actually, so just to maybe to connect this to Fujita, I don't want to look at where L generates. Actually, I want to look at where Kx tensor L generates. You'll see in a minute because Fujita conjecture is about adjoint line bundles. Kx is the canonical divisor of the variety. So Kx tensor L generates SJs at X if this. So this so you tensor that with Kx tensor L and take homology. So if H1 is 0, the previous map is ordered. So now this, of course, is not a convenient sheaf because there is an ideal sheaf here. But blowing it up, we can convert this into the vanishing of a line bundle. Right. So this happens if you just take the pi upon pi. So this is pi upon this. Okay, so I am going to this. I have to sort of mix up the additive and multiplicative notation, but because when you pull it up, it is the ideal sheaf pulls back to the ideal sheaf of the exceptional divisor, which is minus t, so minus s plus 1 times. Yeah. Okay. So this should be okay. Okay. So now we know. So now we can actually work with this and see how to. I mean, there's some standard algebraic geometry formulas here. So if you take the canonical of the block, this is just the pullback of the canonical below plus minus 1. Where n is I didn't mention, but n is the dimension. So when you blow up a point on a n-dimensional variety, the canonical divisor has this of the blow up has this formula. So now if you just put everything together, so this will translate to H1. Okay, so you will have to, I'll write down the upshot. It's not difficult to check this. Okay, so there is pi upper star kx tilde kx will have kx tilde minus n minus 1 e, which will, when added to s plus 1, will give n plus e. Okay. Now this vanishing will give me what I want. And now we recognize this. If you can show that this is ample, for example, then implies my Quadratic vanishing will give us the required vanishing. Canonical plus ample, which one is 0. So then you trace it back and you conclude that K plus L generates S. So the statement that I want to write here, what is the proof? What we just proved that and Seychelles constant that you see there is exactly telling you when this is ample. So if n plus s is strictly less than the Seychelles constant of L, then we conclude that K plus L generates ST. Okay, so now this is all included in Demai's paper. So he was interested in this, and he looked at this, and then he defined special constants. Okay, so and now I will tell you what Fujita Condition is. Okay. So essentially you can see the upshot there, but we can actually prove the proposition when specializing to, let's call this a theorem. So specializing to s equal to 0 and s equal to 0 mainly. So this is the statement. So this is true for all x. This implies kx plus n plus 1 L is globally generated. And the similar argument, though I have to modify this carefully. Because variampleness is not quite S generation. S generation looks at only 1 point. Variampleness, you have to look at 2 points. But we can modify the statement. It's not difficult to conclude this. So this is what am I? So Shadri constant has certain lower bound. You conclude that k plus n plus 1L is globally generated. A slightly bigger bond, it is variant. And this is known as Fujita Condition. What is the conclusions are known as Fujita Condition. So this says that if X is n-dimensional, smooth projective variety as before, L is ample, then Kx plus is globally generated and Kx plus. So those are the two statements. This is a conjecture. This is true for curves because this is classical degree considerations will give you this. This is even in a, you learn this and you learn curve theory at the beginning. So this is let's say classical. N equal to 2, it's a theorem. It's a celebrated theorem of Ryder. It is significantly more difficult. One needs to some 80. So these are another statement. And generally, in higher dimensions, both statements are open. So I think global generation is known, I think, in 3 dimensions, 4 dimensions. I have not looked up the literature, but Ian Lazarfeld, Karen Smith, they have done, among others, have done a lot of work. So this is one of those fundamental questions that I want to emphasize. Okay, so it's fundamental because it's difficult and it seems to be connected to a lot of algebraic geometry. Okay, so now you can see why MI was thinking about this, because one can hope that you prove some bounds like this, you seem to be getting the conclusion of Fujita. So this was he was hoping that something like this can work. But very soon, I mean, this was all happening in early 90s. Very soon, within a year or two of this was shown to be not the case. The bounds don't. Okay, so for example, Miranda So this is early 90s, very soon after this was defined. So the goal is to essentially hope to bound Seychelles constants by some number independent of the point, right? So that seems that is simply not true. So given any and something like this, given any positive real number, there exists a surface X, ample line bundle L, and the point X. The Seychelles constant can not only fail this bound, this is of course arbitrarily small. So if n equal to 2, these bounds will give, and so you can see it's 2 by 3 and 4 by. You want this for all x. See, if you don't have it for all x, then you're at a loss because you can't. Global generation is a statement for all points. So if you do not have this, you can't have this. And of course, this theorem will not give you Fujita. And Miranda proved that that's not possible. Of course, Fujita conjecture is still open, and in fact, it is true for dimension 2. So just that this approach is not useful. Yeah. General varieties. So yeah, so I think one has to think about this, but the fact that this can be very small happens quite, let's say, generally, but all the constructions are specific varieties, so I don't know whether one can prove this. Yeah, any question? Yeah, so this he gave it for surface, but this can be modified to give it for any variety. But the thing is, his construction is very specific. So Manish's question still stands. Can you do it for a general variety of a certain dimension? Can this hold? Okay, so nevertheless, so the point now is that Fujita conjecture cannot be solved using at least this approach on Seychelles constants. However, these were interesting in their own right, and now people are working on this for the last 30 years. There are many interesting questions. So I just want to give a quick idea of how Miranda constructed this. So I was thinking of what to explain, so I thought this would be an interesting example. Without giving too many details, I want to to indicate what kind of things people look at here. So let me just quickly describe what Miranda did. So given a delta, first we choose a large enough integer. So first we choose large enough integer m such that 1 by m is less than delta. So then I want to choose. So the surface he constructs is a rational surface. It's a blow-up of P2. So already you see that it's somewhat special. So what he does is to choose an reduced plane curve. So we want to pick a curve inside the plane, which has some properties. So such that C has a point of multiplicity m. So of course you can do this, and more than that. So there is another curve C prime of same degree, which is also irreducible, reduced, and degree of C prime is C, degree of C. So it is same degree curve such that two things happen. So C and C prime intersect transversely. Okay, so I don't know if this is visible, but I'll just squeeze it in. So C and C prime are they intersect transversely, and the pencils generated by C and C prime consists only of irreducible reduced curves. So this is a technical requirement that is needed for a part that I will actually not explain, but this can be done. So this is simply a dimensional count. So given a large enough degree, you can choose, and you can choose a pair of curves like this, such that they intersect transversely, and any curve which is in the the linear system spanned by them is actually integral. Okay, so now we just do the following. So for now, let's accept this, that there is some, and this is a simple dimension count document. So now we simply blow up the d square points that are in intersection. So let's say d is the degree of this. These are, and they're all smooth points of both C and C prime because the curves be transversely there. So now you can define. So let's say C tilde and C prime tilde are strict transforms of C and C prime. They will be isomorphic to C and C prime because we are blowing up smooth points on those two curves. And let's say E is some exceptional divisor. So let's say P inverse P1. So C. So I don't know if you can see, but one of the points, I take any exceptional divisor. So pullback of the first point. Let's see. Then I define a divisor like this. 2C tilde plus E. So one can check that it is ample. So this is not difficult. This uses the Nakai-Moshizan criteria. We want to show that L square is positive and L dot any curve is positive. So I'll do the easy part. What is L square? It is 2C tilde plus E square. Now C tilde square will be 0 because C tilde square is C tilde times C prime tilde. So these curves are separated. So that will be 0. C tilde dot E will be 1 because the point that we blew up is a simple point on C tilde. So that will give you 4. Right? And mine E square is -1. So that is positive. So one can check now that L dot any curve is positive. I am going to be interested in L dot C tilde. So L dot C tilde, of course, is 2C tilde plus E times C tilde, which will be C tilde times E, because C tilde square is 0. I've done one curve. There are just few more curves that you can check, but it's not difficult to check this. But now, what is I'm going to, let's say point X of multiplicity M. That point is not among the blown up points, so that point has a unique image, which I'll just call X again. Then what is epsilon Lx? In the first definition that we gave, it is the infimum of some ratios. So I can, C tilde is a curve through that point. So it will be L dot C tilde divided by multiplicity of C tilde at X. And by what we just show, this is 1 by n. And this, of course, is. So epsilon Lx is strictly less than delta. One can show that it is actually equal to 1 by m in this case. And show that all rational numbers can be achieved as Seshadri constant, but this anyway gives us what we want. So this example, I hope, conveys the fact that it's not that easy to produce small Seshadri constant. You have to do some very clever constructions. And the point that we have constructed in the whole the line bundle and everything is suggests that even though they can be very small sometimes, maybe there is some general statement, generality. In general, they are actually not that small. Yeah. So, and this is what Ein and others will do. So Miranda's example shows that stationary constants can be very small, but Ein and others will show that if X is a surface, non-singular projective surface as always, L is ample, then the stationary constant is at least 1 for a very general point. Okay, so at this point, we mean what actually they proved is that outside a countable collection of points, it is at least. So this Miranda's example and Einl's theorem give you two sides of the picture. On the one hand, at special points, it can be very small. Of course, this point is a special point you have chosen in the beginning. But at general points, you have a bigger lower bound. It's at least 1. Again, let me remind you that this is not very useful for Fujita, because you only can say that the line bundle is, general point is not in the base locus of the line bundle, which anyway you know. So it's not useful as far as Fujita is concerned, but this is an important structural result about stationary constant. Okay, so I have already used up maybe 30 minutes or more. So yes, that will come up now in the questions. But as of now, no, it's open. So I will move on to questions. I was planning to do examples, but then I'll only do examples. So you have to pick X to be any point, right? For this example, no, I want the curve to have a very high singularity at the point. X to have multiplicity M. Pointing to the curve to that point. So you can take any point, but then you have to do some, how do you find a curve with a high singularity at the point?
Start with the point, then construct the halo. You start with the point and you construct the line.
No. So see, you think of it like this. Does there exist an open set of points where this holds? Or does there exist a, complement of a countable set where this holds? That is the kind of thing that you cannot do.
So, and one more device, there is start with the no. Yeah. They're all equal. So here you start with the point and then you construct the line model. There you start with the line model. Yeah. So the line model is also choose the line model first and then finding the point. And here you start with the point and then construct the line.
Yeah. So the first question is related to Parmu's question. So Nagata conjectured this. It's in his book. The same statement for any variety, any n-dimensional variety, L ample. So then epsilon Lx. Yeah, so everything is smooth for me. Global assumption, non-singular. So by the way, this result is very specific to complex. Okay, so yeah, it's not in general. Epsilon Lx is greater than or equal to 1 for a very general one. Okay, so now this is open in general even for three-dimensional varieties. Though you can prove this in specific types of varieties. You can, I think, maybe toric varieties, abelian varieties, or some other class. There are results. I don't know whether it's completely known, but there are results in those cases. But there is a theorem that epsilon Lx is greater than or equal to 1 by n for a very general point. So that one can show. And this is of course far from 1, and this is fine. So this is the first question that I won't talk much about.
What is the last name?
K-U-C-H-L-E, Kukle. That is how I say it. I remember the question. Okay, so there are several other questions, but the one I want to focus on is related to rationality question. Maybe before that, I'll mention this question also. So for any variety, so let's define epsilon x to be infimum over all pair signs. So L ample. So this you can call Seychelles constant of this variety. You take the Seychelles constants of all ample line bundles at all points and take the infimum. So of course, you know that individually this number is a positive number because of Seychelles criterion for amples. But the infimum can very well be 0. So is there a this is the question. So I think there is not much known about this, though my suspicion is people think that there should be such numbers, even surface.
But Miranda.
So Miranda, because he has to, I mean, this delta determines the surface. So you change delta, then you have to go to a bigger block. So you want this to happen on a single variety. Miranda only gives like a sequence of surfaces. And the other question. Okay, so is it always rational? Okay, now this is suspected not to be the case, but we don't have any example where this is not the case.
In 2,
Yeah.
is there a good class of varieties for which it's always positive?
Yes, so that is for many. Yes, there are some good classes of varieties where this is a positive integer, for example. So this can be some kind of homogeneous varieties with the group action.
I thought so.
I won't say for all of such things, but there are nice classes where these are integers. So then, of course, this will be positive.
Toric varieties and things like that. Again, I mean, asking.
What
Toric varieties.
It is. Yeah, so I don't think this is known for toric varieties. I have to think about it. I don't think it is known to be positive for toric varieties. Yeah, Gmod, yeah, maybe. So again, we look at some equivariant vector bundles, then line bundles, then it's okay, but it's not completely clear about the general situation.
Okay, thanks.
Yeah. Correct. So one can ask this for specific classes of varieties, and that would be interesting. Okay, so now we don't know of any irrational Seychelles constants. So this is what I want to focus on. But provided some conjectures are true, some well-known conjectures, one can show this. Yeah, so that is what I want to use the remaining time for. Now we focus on so in this context, let me now introduce a few conjectures which are very important in this linear systems on plane P2. The first one being Nagata Conjecture, which made at least tangentially and appearance in dispersion talk. So he did not talk about the conjecture of Nagata. He mentioned that Nagata gave a counterexample to Hilbert's 14th problem. So that was the focus for him in that paper. But in that process, he defined some. The example itself led to a lot of work. I mean, in some sense, you can say this is in this 1958 paper of Nagata is the starting point of all this study. Though that was sort of an incidental remark for him because he was interested in some invariant rings and so on. So in the modern language, or even I think this how Nagata stated it. So if you have the conjecture is the following. So if you have a degree D, irreducible reduced curve, I think you may not need this, and let's say the multiplicity of the curve at some, so mi's are some non-negative integers. P1 through PR are general points, or very general points one has to take in general, or what I think Nagata calls independent generic. We'll just be somewhat sloppy about that. So some sufficiently general points. The curve has high multiplicities at those points. Then Nagata says that this ratio D divided by the summation of the multiplicities is greater than 1 over root R. In fact, it's strictly greater than 1 over. And let me also mention that R should be at least 9 here. So this statement is false if R is strictly less than 9. So Nagata made this conjecture. He proved it for squares. Any perfect square, he proved it for 9, 16, 25. And I think the 16 points case is what gives him the example, the 13-dimensional thing that you mentioned. So he was happy with this. He was interested in this counterexample. Just as a sort of incidental remark, he said this should be true in general. He was interested in 16 points and this inequality, but he made it a conjecture for all other R, including the first one. So for 10 points, it is open as of today. So this is an important conjecture. So this is another fundamental thing in algebraic geometry, which is important because partly it is difficult, as you know, for example, in the last 60 years, nobody has in some sense come even close to this, proving this. But also not just because it's difficult, but because it led to a lot of mathematics. So in an attempt to study this, a lot of theory and interesting theorems were put. So if you think about this, Nagata conjecture is a statement about certain linear system being non-empty. Let me think of it like that. So basically, Nagata conjecture says that if that inequality is violated, if D is strictly less, D by summation mi is less than 1 by root R, less than or equal to 1 by root R, there cannot be a degree D curve with those multiplicities. So a certain linear system is non-empty, or rather empty. If some inequality implies a certain linear system is empty. So this is a classical problem that people study. It's called the interpolation problem. So let me. So what is this interpolation problem? So it's basically given D, M1, MR, non-negative integers. D is positive, but MIs are non-negative. And points. Is there a curve? P of degree D, so curve in P2. And multiplicity of C at the points is at least 10. Okay, so this is a classical problem. So given a degree and certain prescribed multiplicities is a curve through those at these prescribed points has the prescribed multiplicity. You can see that some necessary condition or sufficient condition, I would say, for the existence is simply given by dimension count. So if you have, this is the projective space dimension of the degree D curves, degree D plane curves. And any point of multiplicity mi imposes mi plus 1 choose 2 conditions. So if this is strictly more than or greater than or equal to, then of course there will be such a curve, because simply the projective space is non-empty. But sometimes the curve can exist even when this inequality is not satisfied. So very simple example, let's take D to be 2 and I take 2 points. If you calculate this, I get 2 plus 2 choose 2 minus 1. So that is 5. And this number will be 3 choose 2 plus 3 choose 2. So this is not greater than equal to. So, but then let's think about this. Are there conics with 2 double points? So there is such a conic, right? You can simply take the line and take twice. So that's a degree 2 curve with multiplicity 2 at these 2 points. So the dimension inequality is not satisfied, yet there is a curve, right? So the notation is something like this. In general, we look at this. So this is a linear system of degree D curves with mi multiplicity at the R point. So this is not empty yet. But then this curve is of a very specific type. It is actually non-reduced, and the line, so it's twice a line, and that line is also not completely random, because this line, when you blow it up, becomes an exceptional curve, because L square will be minus 1. It's a smooth rational curve on the blow up with self intersection minus 1. Okay. So I'll just do it here, but this need not be. So I want to state the precise conjecture. So there are 4 people. It's Segre, Harmon, Gimilian, and Hershowitz. And this is known as SHGH conjecture. So they all conjectured this independently in more or less equivalent forms. So there are multiple versions of this conjecture, and it is now called SHGH conjecture. So I will just state the one that is mostly useful for us. But orally, let me just say that SHGH conjecture says that any unexpected curve, so think of this as unexpected curve, purely because the dimension count, sort of indicates that it should not exist. So any unexpected curve must be a non-reduced curve of this kind. So it must have multiplicity at least 2 times. So in its base locus, there should be a curve, multiple component of some exceptional curve. So that is what SHGH conjecture says. But the version I want to state today is this. So let's say X is a block of R general points. Then there are 2 statements in SHGH. If C is an irreducible reduced curve with C square is less self-intersection less than 0, that means it's a negative curve. Then C square must in fact be minus 1 and C is isomorphic to P1. So the only negative curves on a block are exceptional curves of the first kind. So, blow up of this one. So this version will not look like the one I'm mentioning, but this is what I want to say. If B is an F and effective divisor, then B is not special, meaning its dimension, linear system of dimension will be exactly what you would expect. So there is okay, so this number will be mysterious, but it simply says that D is not special. If you write D as the pullback of the divisor D and Mi is being multiplicities, this is exactly the dimension that I just erased, the expected dimension. Okay, so now this is the second conjecture that I wanted to state. I have 10 minutes. Okay. So the third conjecture, so this is called weak SHGH, is just the statement 1. So the first statement. So the three conjectures. So if C was special or not? What was C is any irreducible and reduced curve. So this is sort of independent statements. So one is classical. Yeah, meaning people would have thought about this. It's that way. No, this statement is not classical. I mean that there are no negative curves other than this on a blow. I mean, maybe Caslow thought about this, but it's not clear. I don't think it was written down. Zariski may have thought about this, but yeah, I don't think there was any serious work on this. Let's say. Okay, so yeah, so 1 and 2 are somewhat unrelated statements. So clearly, SHGH implies weak SHGH, and also it's actually weak SHGH implies Nagata. Okay. So that is the implications along this theory. So let me just try to quickly give a proof of this, because this is a very nice argument and it's not difficult. So Nagata is somewhere there. Yeah. So suppose Nagata conjecture is false. So Nagata conjecture is false means what? That there is a curve that violates that inequality. Right? Let me just see this. So say C violates. So I'll go fast at this point. So C violates Nagata conjecture means C is a degree D curve with multiplicities being Mi and T. Correct? And R is at least 9. So we have this. So I'm sort of not writing the full notation, but you have a degree D curve. Yes, thank you. 1 over. So how will I get into this setup? So I want to do this. So, but then you consider the block strict transform of C. So then standard blow-up theory will tell you that this is where H is the pullback of O1 and EIs are the exceptional divisors. So I'm blowing up the P points, R points. So now C tilde is this, and C tilde square will be D square minus summation Mi square. The way intersection product works on the block, H dot EI is 0, EI dot EJ is 0 for I not equal to J, and EI square is -1, and H square is 1. So you get this. And this is actually negative. So this comes from this. This is some standard Cauchy-Schwarz type. So C tilde is a negative curve. Now weak SHGH implies C tilde is of course -1, but it's also P1, so that means K dot C tilde is -1. So minus K dot C tilde is 1, the canonical term of that. So this is the genus formula. If it's P1, if and only if this happens. So I just want to write down what this means. So this is actually nothing but 3D minus summation mi. Because Kx tilde is 3h minus E1 plus E2 plus Er. So if you write it out, this is what you get. So 3D equals 1 plus summation mi. But 1 plus, or rather I want to write this as, sorry, so I'm almost done. Summation mi is, let's see, 3D minus 1. So this is 1. So this is 3D minus 1, but D is less than or equal to summation mi by root r let me just go through. So this is less than or equal to root r d minus 1, because 3 is at least, r is at least 9, so root r is at least d. And root r d is less than summation mi. So that's your contradiction, because mi is less. So SHGH implies weak SHGH, which implies Nagata. So this is the conjectures. So let me now end with 2 minutes. So now there was a theorem. For people, December. So they showed that if SHGH conjecture holds for r plus 1 points, but SHGH conjecture that I erased is a statement about r point block. So if it holds for a particular r plus 1, then there exists an ample line bundle L on r point block such that epsilon Lx is not in fashion for some x or a general x something. Let me just say for some x. So if SHGH conjecture holds for 10 points, let's say, then on the 9-point block you can produce a irrational Session constant. So they use the full SHGH. Now Brian Harborn and I, we improved this, the same statement, assuming not all of SHGH, but weak SHGH. So if the weak SHGH conjecture is true for r plus 1 points, one can produce an irrational Session constant on r point. And the final thing I'll say is, so this was the original theorem. This implies irrational Session constant. We proved this, but one can, if the next question would be, can you prove the same result, similar result with Nagata conjecture as your hypothesis? And the advantage of Nagata conjecture is that it is actually proved in some cases. So for example, it is known for 16 points. So if one can prove a result, the same statement, but assuming Nagata conjecture, then on a 15-point block, you can produce an irrational Session constant, and that will not be a conjectural statement. It will be an absolute statement. So obviously that is difficult. So one can try to prove this result with Nagata conjecture, but that's not. Its difficulty level is similar to producing irrational Session constant, which nobody has done. But this is an interesting problem. Okay, so I think I'll stop here. Thank you.
For surfaces of general type, can you say something about stationary constants? Something interesting there.
So there are some, yes, there are some results on them. I mean, interesting. So people have looked at stationary constants for line bundles and surface of general type. So, so the answer to your question is it has been studied. So I don't think there's nothing striking that I remember right now. So there are lots of results for stationary constants on different kinds of surfaces or higher dimensionality. So each case takes its own form. There's no sort of overarching result like greater than or equal to 1, like Ein-Lazar's result. On any surface, epsilon Lx is greater than or equal to 1 for a general point x. That's a very nice global statement. So after that, most results are specific to a type of variety, abelian surfaces or varieties, general type surfaces also.
Form lower bounds?
Yeah, form lower bounds, some precise calculations in some cases. So, and there are nice conjectures. For example, if you take a degree D hypersurface in P3, for D at least 5, that's a general type surface. So for a general degree D hypersurface of D at least 5, stationary constant for the O1 is conjecture to be root D. So that also is another candidate for an irrational stationary. But we don't really.
That will prove Fujita Condition.
How that statement will prove Fujita Condition.
Root D is greater than.
Yes, correct. At least the so it will give an proof for both of those and two statements. Yeah.
Explicit computation is known also that can you say that it will be to irrationally or able to say back.
Yeah, it will be. Yeah, so because the stationary constant, I didn't have time to talk about all this, has a bound like this. Always. So the square root of the self-intersection. And if it is a strict inequality, so this is always true. And if epsilon is strictly less than L square, this implies epsilon Lx is rational. Okay, so the irrational stationary constant would be equal to square root L square. So we give a specific ample line bundle for which stationary constant is equal to root 6 square.
However, conversely, for any given rational number, can you produce ample line bundle such that the stationary constant is that?
Yeah, that you can do. So given any positive rational number, you can produce a XL and a point which will have the stationary constant equal to that. So this is related to the Miranda's example I gave earlier. That less than 1 by m, in fact, becomes 1 by m. So you can achieve 1 by m. Then by taking a multiple of L, you can get n by m. That is not it. All rational numbers can be achieved. But you have to change the variety. Yeah. No. So this in this theorem, we produce a line bundle. In fact, lots of line bundles where stationary constant is equal to root L square, and L square is not a perfect square. So conjecturally, of course, if we can say so one of those examples, I don't remember precisely, but L square is 6 in that example. So the stationary constant is root 6. Is equal to root 6.
I thought irrationality. Oh,
assuming this. Yeah, this is. I mean, even Nagata conjecture is not known, so we just assume something stronger than and good. So this is only conjecture.
But it will always be some square stuff.
If you also vary the generic line bundles, there is some statements like in higher dimensions, except for MEL. Suppose there was a general line bundle is less than or equal to 1.
Yeah, so I don't know. And your square root of it?
Rational number.
It will be a square. If it is irrational, it will be square root of a rational. Because it is square root L square. In fact, it will be square root of an integer. On a surface, the possible values of stationary constants are either rational or quadratic. Root of integer. Higher dimensional varieties, it can be cube roots. They will all be algebraic. So that is the thing. Stationary constants are algebraic.
Similar thing like from L square you get L power n in the
L power n, so it will be nth root of n.
There are no further questions. Thank you. Yeah, we are going to go before having done here at 2 o'clock. Can I ask whether